So as you can tell by the title slide, today we're going to be talking about the pigeonhole principle. So whether you have no idea what that is or have already heard of it before, we're definitely going to start by going over at least what exactly does that mean, and then we're going to some problems about it. So even if you've heard about it, there'll be some interesting problems for you to think about. So this is what the pigeonhole principle says, or at least a version of it. So I'll just read it out. If we have n plus 1 pigeons and n holes, there will be some hole with at least 2 pigeons inside of it. So this may sound kind of formal, but if you really think about it, it just makes sense. So if you have n holes and you want to put the pigeons in those holes, obviously there are going to be 2 pigeons inside one of the holes, or maybe more, because you just have more pigeons than holes. That's really what it's just getting at. So we can prove this formally. Formally, this is called a proof by contradiction, but even if you're not quite sure what that is, you can just reason through this. So just to get through this theorem formally, we can first assume that each of the n holes, they're n holes, we say they all have at most 1 pigeon in them. So we're assuming the opposite of what we're trying to prove. We're saying that there should be at least 2 pigeons inside a hole. We're saying the opposite of that is that they at max have 1 per hole. So if each hole has a maximum of 1 pigeon, then that means that the total number of pigeons, the maximum number of pigeons we could have, is 1 plus 1 plus 1 n times, right? Because there are n holes, 1 pigeon per hole, so n pigeons should be our max. But that's a contradiction because we said we have n plus 1 pigeons here. So because we have a contradiction, this initial assumption that at most 1 pigeon is inside the hole must be false. So if this initial assumption is wrong, what I'm highlighting right now is wrong, then what we want it to be true, that there's some hole with at least 2 pigeons in it, must be true. So this is like a formal proof of this theorem. It should make intuitive sense. So, you have 2 pigeons, let's say 1 hole, they're going to have to share that hole. Now, there are some other ways of stating the pigeonhole principle. That's kind of the simplest form. But this is a more abstract way of saying it, and it's more generalized, so it'll help you with problems that get a little bit more difficult. You have a sequence of n positive integers, and then you add them all up. So this is adding them all up here, and then you subtract n and add 1. And that's how many objects you have. So in the analogy of pigeons and holes, you can think of the objects as the pigeons and the boxes as the holes. So you're putting that many objects or pigeons into n boxes or holes, and then we're saying that the first box contains at least q sub 1 pigeons, the second box contains q2 pigeons, and so on. Again, we proceed by something called a proof by contradiction. So when we do proof by contradiction, we just assume the opposite and then try to find something that doesn't make sense, some sort of contradiction. So if we assume the opposite, that means that every box has at most qi minus 1 objects. We said first box has q1 objects, so now we're saying at most q1 minus 1. The second box, we hope to find q2 objects, so now we change that to q2 minus 1. So we kind of just go 1 lower. And then now our goal is to try to find some sort of statement that doesn't make sense. So along this train of logic and thought, we're trying to find something that's wrong. So similarly, it's actually quite similar to the proof that we just did. So you consider, now that you've put this restraint on your holes or boxes in this case, you want to find what is the maximum number of objects, or in other words, pigeons you can have. So the maximum number, as we said here, is qi minus 1. So we just plug that in, and we get q1 minus 1, q2 minus 1, all the way up till qn minus 1. We just add them up. And then what you get is the sum of the q's minus n. This minus n comes from the fact that we have minus 1 n times. So minus 1, minus 1, minus 1 n times is minus n. However, this is a contradiction once again, because it is less than the number of objects that we had. We said that we had q1 up till qn minus n plus 1 objects. However, this doesn't have the plus 1, so we're 1 short. So that's our contradiction, so this must be true. And again, just describing some vocab, you'll notice that it says corollary here. So that's kind of a term used in math a lot. So really what that just means is that it kind of follows for something we did previously. So we previously talked about a version of the pigeonhole And this one being so similar, we can call it corollary because it follows from that. So now we have another corollary, and this will be near the end of some of the abstract stuff we do. So if we have P pigeons and H holes, then some hole contains the ceiling of P over H pigeons. So this is a more strong definition. I first started with just n and n plus 1, and this is just more general. So we're trying to build up a more strong definition of pigeonhole, and then from there, we can apply this to some problems. So I'll definitely note that this proof is more complex than the other two. And generally speaking, while the proofs are definitely great to understand, we do want to stress that it is more important really that you focus on the problems, I think. So this proof might be a little complex, but I'll walk us through it. So we're trying to place the pigeons in the hole so that we don't have the ceiling of P over H in any one hole. So again, this is that same kind of idea from before where we're trying to assume the opposite and then end up getting to something that's wrong. So we're going to go about this process in an attempt to not find this hole, but then we'll show no matter what, we end up having that hole. So there's this thing called division algorithm. Basically, it's a way of rewriting a number. So you can write P as HQ plus R. So basically, you can take Q, multiply it a bunch of times. By a bunch of times, I mean H. And then there's going to be some remainder left over, at least in the case that P is on a multiple of Q. So that remainder is R. So there's a reason why it's called Q and R. This is quotient and remainder. So this is really, you can think of it as like division almost. That's why it's called a division algorithm. So this is the remainder, this is the quotient. And then because it's a remainder, it has this inequality property. And then you should observe that Q, so this quotient here, is equal to the floor of P over H. So Q really just means how many times does Q go into P. So for example, how many times does 3 go into 10? So you have 3, 6, then 9. So it goes in 3 times. And then you can also notice that 10 divided by 3 is 3 1/3. Take the floor, you get 3. And that's what we wanted. So this is just P over H, so you do the division to get your quotient. And then the reason we take the floor is just so we deal with an integer. So if you remember, the floor just chops off that fractional decimal part, and that's exactly what we're looking for. So that's why we use the floor here. So if R equals 0, then we actually know that the floor is equal to the ceiling. So this is because if you think about it, let's say we're essentially dealing with the floors and ceilings of integers. Because if this is the case, if R equals 0, then P is actually a multiple of Q. So if we just, let's do a numerical example with multiples. So let's say you have 7 and 14. So if you take 14 divided by 7, that's P over H, you get 2. So the floor of 2 is just 2. It is no fractional part, so there's nothing to chop off. So you get 2. The ceiling of 2 is also 2, because there, again, is no fractional part, so you're just stuck at 2. So whenever you're dealing with integers, the floor and ceiling are exactly the same. So then here we're done. So we found our hole, that's the ceiling, because the floor essentially is the ceiling. Now, sorry for the typo, this should say R. But if R is greater than 0, if the remainder is greater than 0, then there's at least one hole with the floor of P over H plus 1 pigeons in it. And this is actually equal to the ceiling. So again, we can do a numerical example. So let's say you take 3.4. The floor of 3.4 is 3, and then you add 1 to get 4. And the ceiling of 3.4 would be 4. So whenever you have some sort of fractional part, taking the floor and adding 1 is the same thing as just taking the ceiling. So regardless of whether R is 0 or bigger than 0, we find our hole that has P over H pigeons. So now that we've gone to some of the theory of pigeonhole principle, what it means, now we're going to work on some problems. So this first one, it's a little bit more straightforward, but it should get us used to dealing with the pigeonhole principle. So I'll just read it out, and then maybe we can take some time to think to ourselves what the approach might be. So we have a school of 6 students, and then the school policy states that students can only wear blue, green, red, black, or white shirts. And you want to prove that every day there will be at least 2 students wearing the same color shirt. So this is straight up applying Pigeonhole. So we have 6 students. So you can think of, so you have 6 students and you have 5 different colored shirts. So therefore, there are going to be at least students wearing the same colored shirt. So this is kind of like the first statement. So I'll just flip back really quickly. So this is like if you have n+1 colored shirts, and then, sorry, you have n+1 students and then colored shirts, then there's going to be 2 people wearing the same colored shirt. So, all right, so let's move on to the next problem. So this is definitely more complicated. It is not just simply just, you know, plugging in. You have to be a little bit smart about this. I'll just read out the problem. Prove that if we color a plane with the colors blue and red, there must be 2 points of the same color that are 1 unit apart. All right. So I think we'll drop the hint now. So the hint is to draw an equilateral triangle of length 1. Yeah, so the idea, you know, you draw the triangle with side length 1. You have 3 vertices, but you only have 2 colors. So then you're going to find 2 of the colors, which will have the same color, which, as Michael said before. This is a classic problem. I remember this one. So if you have an n by n board filled with the numbers -1, 0, and 1, such that the sums along all rows, columns, and main 2 diagonals are all different for each other. So the hint, think about the number of possible sums. So for any n, how many possible sums are there? And how many rows, columns, and diagonals there are. So just think about how many options you have for those two things: the number of sums, and essentially like how many times you're going to compute the sum. So the rows, columns, and diagonals, main diagonals, that is. The possible sums is between -n and n, and that's because, as Michael said, if you want to minimize everything, you take the smallest number you have, -1, you add that n times, you get -n. Same logic for positive n, and the number of integers there are 2n plus 1, because you have 1 through n, -1 through -n, and then the +1, you got to remember 0. Number of rows, columns, it's n plus 2, as Michael said. So then by the Pigeonhole principle, there are at least 2 rows, columns, or main diagonals that have the same sum.
Okay, great. So I assume that perhaps some of you have been thinking about this problem like during the break. And so just like I'll provide just like a hint on what to do next, just to see like essentially like how you would approach this problem. So perhaps some of you can think about splitting the unit square into 4 equal subsquares. Okay, great. So let's actually just go into the solution right now. So after we divide the unit square into 4 subsquares, you can notice that by Pigeonhole, since we're placing 5 points into this square, there will be at least 2 dots in the same subsquare. And so you can notice that the longest distance in each subsquare is square root of 2 over 2, which is essentially just the diagonal of each of these subsquares. And you can verify that for yourself. And so that essentially proves the claim. Okay, awesome. So problem 5 states that in a 10 by 10 square, there are 101 points such that no 3 of these points lie on a line. And we want to prove that some of 3 of these points form a triangle whose area does not exceed 1. So again, let's try and like remember, you know, try and figure out like, you know, what we want as our pigeons and what we want as our holes. And I think that'll help a lot of you just figure out the solution.
All right, so you'll note this is a similar theme in terms of taking what you have and then splitting it into smaller things. Solution for this problem now.
Yeah. So if we took our hint of, you know, splitting the square into 50 2x1 subrectangles, then by the Pigeonhole principle, we can say that there will be at least 1 subrectangle with 3 points in it. And now you have to notice that the maximum area of a triangle that's contained in a subrectangle is 1. And so we first have to understand like why this is the case. So we understand that the area of a triangle is given by base times height divided by 2, right? And so when we take a subrectangle that's whose dimensions are 2 by 1, the largest triangle we're going to be able to fit in there is just half the area of that subrectangle. And that's because the longest base we can have and the longest height we can have is 2 and 1 respectively. And so that's kind of the idea behind it. And so that essentially shows that that we can there will always be 3 points that form a triangle whose area does not exceed 1. And I think based on a lot of your comments in the chat, a common misconception some of you are making is about like what Pigeonhole tells us about the distribution of points. So problem 6 asks that us to prove that if we draw 9 lines within a square such that each of these lines divides the square into 2 regions of area in ratio 2 to 3, then 3 of these lines will be concurrent. So again, just to reiterate, let's try and figure out like where how we want what we want our holes to be, and how can they give us essentially like how can they give us our desired results. So let's go into the solution. So let's say we take a vertical line that divides the square into 2 regions of area 2 to 3, and this is just a line that I constructed FE. And so we should notice that our vertical lines must go through point G, and that in fact that any point that essentially divides the square into regions of area with ratio 2 to 3 actually has to go through point G, which is the midpoint of FE. And so why is this the case? What you can notice here is that in line HI, we see that this triangular region is equal to this triangular region, right? And so we're essentially keeping the ratios of the area the same, because we're essentially, as we rotate the line around G, we're keeping the areas the same. We're essentially trading one piece of area for another piece of area. Suppose we take this as one of our areas, the area of quadrilateral HCDI, and we compare it to quadrilateral AIHB. We see that this area, the area of triangle IFG, is interchangeable for the area of GEH because these triangles are congruent, or in other words, they're basically the same, and so they have the same area, and so we're essentially just trading areas. So I hope that makes sense. And so and then we have to notice that there's actually 4 of these types of points. So 4 of like our point G's. And so why is that the case? So we can construct a vertical line EF here, and then we can also construct one just shifted to the right, because we're not splitting our square into areas 1 to 1. We're actually splitting them into 2 to 3. So I can create one here that splits this side into 2 and this side into 3. As well as if I shift it over, I can create another line here. But I can also create 2 horizontal lines like that split it into 2 to 3. And you'll notice that if I take the midpoints of each of these 4 lines, our lines have to go through those points, just because, at least one of those points, just because of this whole idea of like trading areas that I talked about. And so this is where we invoke Pigeonhole. Since there are 4 types of our point G, we can notice that if we draw 9 lines by Pigeonhole principle, 3 of them must go through one of our desired points. And I believe Michael is drawing some new points. There's actually 4. And so this is essentially the idea. So problem 7 says 41 rooks are placed on a 10 by 10 chessboard. Prove that there are 5 rooks who do not attack each other. So for those of you who don't play chess, I thought I would explain this a little bit. So essentially, when we have a 10 by 10 chessboard, we're essentially we have a 10 by 10 grid with 100 squares in it, and we place a piece in each of these squares. And what a rook does is a rook can move horizontally and vertically. And so essentially we're trying to show that wherever we place these 41 rooks, we'll always be able to identify 5 rooks that don't attack each other. The overarching branch of this proof is that we're trying to construct 5 rooks that do not attack each other. So the whole idea is that none of these rooks will be in the same row or column. So we can say by the pigeonhole principle, there exists a row on the chessboard such that there are at least 5 rooks in it. And so let's just make sure like why this is true. So we're essentially looking at rows. And so this is the whole idea that comes back to corollary 2, that if we take 41 and we divide it by 10, that's 4.1, and then take the ceiling, that's 5. And so there will at least be one row in the chessboard that contains at least 5 rooks in it. And so we'll call that row A. And so now let's think about it in some sense that we completely remove row A for the sake of argument. So now we have at least 31 rooks and 9 rows. And so I'll explain why we have 31 rooks, or at least 31 rooks. So notice that since this is a 10 by 10 chessboard, a row can have at most 10 rooks, right? So when we remove row A, we're kind of accounting for the worst case scenario, in the sense that there are 10 rooks in that row. And so if we remove row A, we'll be left with 31 rooks. And of course, when we remove one row from 10 rows, we get 9 rows. And so now this is the idea of applying pigeonhole principle again. Now we can show that by applying that same corollary 2, there will be at least one row that contains at least 4 rooks in it. And we will call that row B. Now we remove row B, and we say that there are at least 21 rooks and 8 rows. And so the same idea that we assume the worst case scenario for row B, we assume that there can be up to 10 rooks in that row. And so we will remove it for the sake of argument. And we apply pigeonhole principle again to these 21 rooks and 8 rows. So there exists a row C with at least 3 rooks. And now we remove row C again, and we have at least 11 rooks and 7 rows. So applying corollary 2 again, one row contains at least 2 rooks. We will call this row D, and then we'll remove it again. And then we'll finally consider a last row with at least 1 rook, because we took away 10 rooks for the worst case scenario. And so it'll have at least 1 rook, and we'll call this row E. A thing to make sure we understand here is that what we're considering as our pigeons and our holes, our pigeons are our rooks, and our holes are essentially the number of rows we have left, right? And so we're essentially showing that we can construct some rows with at least 5 rooks, at least 4 rooks, at least 3 rooks, at least 2 rooks, and at least 1 rook. And now this next slide is going to explain why that whole thing is useful. So after showing like what we showed in the last slide, we want to construct our 5 desired rooks. So we'll take a row. We'll choose any row. We'll choose any rook that we call R1 from row E, which we know exists because row E we showed has at least 1 rook. So this is essentially we'll take this, right? And this is just this diagram at the bottom is completely hypothetical. I'll show it at the end like why we can have many different forms. And so what we do next is we choose a rook R2 from row D, such that it does not attack rook R1. And so we know that this rook exists because there are at least 2 rooks in row D. And so if one of them is essentially in the same column as rook R1, we can essentially just choose the other one. And so that'll be our rook R2. And then from row C, which we showed has at least 3 rooks, we'll choose rook R3, such that it does not attack the 2 previous rooks we chose, R2 and R1. And again, notice that we can do this because we have at least 3 rooks in row C. So let's say in our worst case scenario, in row C, there exists a rook that is in the same column as R1 and a rook that's in the same column as R2. So it attacks both of those. But we have 3 rooks, so we can definitely find another rook in that row such that it does not attack R2 or R1, meaning it'll be in a different column than R2 and R1. And then we do the same thing from choosing a rook R4 in row B, such that it does not attack rooks R1, R2, and R3. And then we choose rook R5 in row A, such that it does not attack the previous 4 rooks. And you can see we essentially just created 5 rooks that don't attack each other in this scenario. at the end of these presentations, we have 2 homework problems. So just check them out, put feedback. We hope to see you again tomorrow.